Assalamu alaikum wa rahmatullahi wa barakatuhu. Rabbi yassir wa la ta'assir wa tammim bil khair. So in this video we will continuing with our topic of induction motor. So far we have seen the equivalent model of the induction motor, and we have seen that very closely that its more equivalent model is very closely resembles to the transformers equivalent model, and mostly all the parameters are the same, except that instead of the secondary we have the secondary shorted, and then we have the relative motion which is involved in terms of slip. Now we look at the power and torque in induction motors. So an induction motor can be basically a rotating transformer. So its input is a three-phase system of voltages and currents, and for an ordinary transformer the output is electric power from the secondary windings. The secondary windings in the induction motor, the rotor are shorted out, so no electrical output exists from the normal induction motors. Instead the output is mechanical. So here we can see that we have this input, electrical input to the induction motor, and these are the stator copper losses and core losses which are on the stator, and then we have the transformation of power through air gap, which we call it as the air gap power, and then it goes to the rotor copper losses, and similarly then the power is converted into mechanical, and then we have this mechanical power conversion is induced torque into the omega m, and where we have the friction and windage losses. So friction is because of the bearings, and windage because it is rotating, and then there are some other miscellaneous losses which we cannot measure properly, so we just put them in the stray losses, and then we will have some output power. So that will be the load torque times the omega m. So that's why just like in the transformer we have this P out in the forms of electrical, but here in the induction motor we have this output power in the form of a mechanical power. So we can visualize this equivalent circuit of the induction motor. Here it is very simple. We have called this current as the I1, and which is equal to the V phase over all this impedance Z equivalent. So Z equivalent is can be easily find out. Actually, this is in this equation it is done in only one step. So you can do it in multiple steps, and then it would be okay for you. But still, you can recognize it very easily. So these are in series with it, and then this portion. Here we can see that these two parameters R2 by S plus JX2, they are in series and they by themselves in parallel, so that's why we just use them as GC and JBM. They are reciprocal quantities, and then we have added them, and then you can solve it completely. I think so it's quite easy. This is a basic circuit example. So then we have the stator copper losses are defined as because they are on the stator side. So here is a stator side. So we have 3I1 square R1. 3 is always remember because it's a three phase, and the core losses are 3E1 square GC. Because of this we have these core losses. Similarly, the air gap power then will be input power minus stator copper losses minus core power, and we can write it as 3I1 I2 square R2 by S. Similarly, rotor copper losses can be found out by 3IR square RR is equal to 3I2 square R2. So power converted from electrical to mechanical, so that is P converted is equal to P air gap minus P rotor copper losses. Similarly, that's been manipulated, and we can find out that this 3I2 square R2 by S minus these rotor copper losses, and then we can redistribute these elements to find out in this form. So that will be 3I2 square R2 into 1 minus S by S. So this is a simple manipulation, algebraic manipulation. So now we can see here that power rotor copper losses is equal to S times air gap power. So at S is equal to 0, rotor copper losses are 0, and S is equal to 1, rotor copper losses are equal to air gap power. So always remember that S is equal to 0 means that rotor is rotating at synchronous speed, and S equal to 1, that motor is, we have supplied the three phase to the stator, but rotor is not rotating at all. So that's why all the power of the air gap power will be same as the rotor copper losses. So obviously that's what we have discussed previously, that why this is not good if our motor is means motor is halted for a long time, so it may burn the motor windings. Now power converted, as we know that P air gap minus P copper losses, and this is rotor copper loss is equal to S times or slip times the air gap power. So we can write it in this form, power converted is equal to 1 minus S air gap power, and then we have the output power, which will be the power conversion minus friction and windage losses minus miscellaneous losses. Then this will be the our output power. So the induced torque in the machine is defined as the torque generated by the internal electric to mechanical power conversion. So this torque differs from the torque actually available at the terminals of the motor by an amount equal to the friction and windage torques in the torque. So we can say that torque induced is equal to power converted over omega m. So this is the, remember, this is the developed torque of the machine. So we can write it in other forms, 1 minus S into P air gap, or divided by 1 minus S omega synchronous. So that will be P air gap over omega synchronous. So these both terminologies, both these equations are same, and will give us the induced torque, which is known as the developed torque of the machine. So I hope you have understood till this point. So we will look at the torque speed characteristics in the next video. Still, if you have any questions in this topic, please feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuh.